This is Cladosporium sphaerospermum. Super catchy name, I know. Now at first glance it looks just like a black smudge, a fungus you'd probably ordinarily have absolutely no interest in, and I wouldn't blame you. In fact, right now you're probably thinking, Brad, this is supposed to be a space channel and you've just opened the video talking about fungus. But stick with me, because Cladosporium sphaerospermum isn't an ordinary fungus. In fact, it's not even an ordinary life form. It does something no other organism can, at least as far as we're aware. It can eat radiation. Deadly ionising radiation that rips DNA apart and kills virtually every other living thing down to an atomic level. This fungus doesn't just tolerate it either. It actually uses this radiation as fuel. Now, scientists first discovered it growing on the walls inside the wrecked Reactor 4 building at Chernobyl, one of the most deadly radioactive places on Earth. This fungus somehow evolved and adapted to literally consume radiation in a process scientists have called radiosynthesis. Now, a mutant radioactive fungus found in an abandoned wrecked nuclear power plant. You'd be forgiven for thinking this is some sort of very unserious, weird, clickbaity science fiction video. But this is very real. And more importantly, it has some pretty exciting implications for space travel, but more so colonisation. And that's not just me saying it either. NASA thinks so too. So much so, they actually took a sample of this fungus up to the ISS in 2018 for further study. Now, why? Because this weird radiation-eating fungus might actually help us solve one of the more difficult challenges of space exploration, but more so the colonisation of other worlds. Now, this is the story of the mutant Chernobyl fungus that could actually be the key to living on and maybe even terraforming Mars. If you wanted to design a planet to kill humans slowly, you'd end up with something a lot like Mars. Now, it's dry, frozen, and starved of an atmosphere. But the real killer, at least from a long-term colonisation standpoint, is the invisible rain of cosmic radiation. Now, on Earth, we're protected not only by a thick atmosphere, but also a big, strong magnetic field that acts as an invisible shield. Now, it protects us by deflecting most high-energy particles from the sun and deep space. Now, Mars, however, it just doesn't have that. Its magnetic field collapsed billions of years ago, and what's left of its atmosphere is around 100 times thinner than Earth's. Now that means every square centimetre of the Martian surface is constantly bombarded by a blizzard of ionising particles. Protons and heavy ions, as well as secondary particles like neutrons, moving at nearly the speed of light. Now, a human on the surface of Mars would absorb about 230 millisieverts of radiation per year. Now, for reference, that's the equivalent of around 2,300 chest x-rays every single year. Now, that's enough to roughly double your lifetime risk of cancer, as well as quietly shredding your DNA and causing a myriad of other health issues over time. It's bad. So for astronauts, the question isn't, can we go to Mars? It's more like, can we survive it long enough to stay long term? Now, radiation doesn't just damage biological matter either. Technology also isn't safe. It degrades electronics, weakens materials, and complicates pretty much every engineering system we'd rely on to stay alive. Now, our best current solutions look like thick layers of lead, polyethylene, or more in situ resource utilisation methods like using the Martian regolith, basically building habitats under the dirt or underground for protection. Effective, yes, but heavy, static, and prone to cracking or erosion in dust storms. And once damaged, they obviously don't repair themselves. So what if they're a material that could grow, heal, and adapt? And more than just protection too. Something that could use that deadly radiation to prime the Martian soil for agriculture and eventually terraforming, taking one of Mars' greatest weaknesses and turning it into one of its greatest strengths, at least in terms of human colonisation. Strange as it sounds, such a thing actually already exists on Earth. Now, some years after the Chernobyl disaster, teams of Ukrainian and American scientists began studying the strange ecosystems that had started to reappear in the Chernobyl zone of alienation, essentially the no-go exclusion zone around Chernobyl and the surrounding irradiated areas. Now, among them was Professor Nelly Zhdanova, a mycologist or fungal specialist. Now, what her team discovered inside the damaged reactor building was both a little unsettling but also incredibly fascinating. Thick black fungal mats growing on the concrete, the pipes and other wet surfaces inside the shelter. Now, by all accounts, this should have been impossible. The radiation present in this environment is death to all biological life, with very rare exemption. At least by our understanding up to that point in time anyway. Now, these obviously weren't ordinary fungi. They were dark, almost oily looking and rich in melanin, the same pigment that gives colour to human skin, hair and eyes. Now, with a combination of both fascination and disbelief, samples of this fungi were taken back to a lab for further testing. And upon doing so, scientists found something utterly bizarre. When exposed to radiation, the fungi didn't die. They actually grew faster. And even more oddly, their hyphae, the long filament-like structures fungi use to grow, seem to actually orient themselves towards radioactive sources, like they were actively reaching for it. Sort of in the same way sunflowers exhibit heliotropism, where they turn to face the sun throughout the day to help maximise photosynthesis. When studied, Cladosporium sphaerospermum's hyphae actually actively oriented themselves towards sources of radiation in a process these scientists labelled radiotropism. A later work by researchers such as Ekaterina Dadachova and Arturo Casadevall in the early 2000s confirmed that something never before seen was indeed happening here. Now, when they studied these melanised fungi, including samples of Cladosporium sphaerospermum and Cryptococcus neoformans, they found that ionising radiation actually changed the structure of the melanin molecules. Now, this change boosted electron transport, or the flow of electrons within cells, and sped up metabolism. In other words, the fungi seem to be harvesting energy from the radiation, not photosynthesis or chemical oxidation, something brand new and never before seen: radiosynthesis. Think about that for a second. An organism born from one of humanity's worst disasters, evolving to eat the very radiation that caused it. Perhaps best described in the immortal words of Ian Malcolm.
Life finds a way.
But this wasn't a Spielberg movie. It was peer-reviewed, repeatable biology. And that made scientists, especially the ones who think about Mars colonisation, pay very close attention. So how does a fungus feed on radiation exactly? How is that even possible? Well, to break it down into simple terms, melanin, the pigment inside these fungi, is an incredibly complex molecule. It's made of long chains of aromatic rings. Think of them like loops that can trap and move electrons. Now, when radiation hits melanin, it changes the spin state of some of those electrons, essentially knocking them into a higher energy configuration. Now, the fungi seem to use this energy boost to enhance metabolic reactions, like charging a tiny biological battery. Now, it's not photosynthesis. There's no light harvesting pigment like chlorophyll in a regular plant. It's more like a trickle charger. Radiation gives the fungus a metabolic edge, helping it grow faster than it otherwise could. And it turns out this isn't just useful for surviving Chernobyl. It might actually be exactly what we need to survive Mars, or at least help. Now, in 2018, a team of student researchers partnered with NASA to send samples of Cladosporium sphaerospermum to the ISS, or International Space Station, for further study in space. Now, they grew it inside a small cube lab module called Space Tango to see whether it could live and possibly protect in orbit. Now, they placed radiation detectors under a thin 1.7mm layer of fungal biomass and compared it to a control sample without the fungus. Now, over 30 days, they recorded a measurable drop in radiation underneath the fungal layer, about 2.17% less exposure. Now, 2.17% admittedly doesn't sound like much, but that was with a 1.7mm layer, which is that much. So if we simply extrapolate it out, a layer about 21 centimetres thick, or 8¼ inches for my American friends, could potentially halve radiation levels on the Martian surface. Half. That's not trivial. It's a significant reduction. And unlike lead or aluminium, this shield would be growing and self-repairing. Just feed it a little sugar and water and let it do its thing. Even better, the main ingredient in this fungus, carbon, could be sourced on site from Martian CO2. In theory, you could literally grow your own radiation shield. And that's not my line. That's how NASA researchers themselves describe the potential of this experiment. Now, it's elegant, as much as fungi can be, self-sustaining and adaptive. Everything that static materials just aren't. And it's also incredibly lightweight because you only need to take a very small amount with you, then grow the rest when you get there. Now, this here is a huge advantage on its own. The payload cost to Mars is astronomically expensive. Now, whilst SpaceX are aiming to dramatically reduce this, until that happens, or if it does, based on recent actual missions, the cost per kilo of payload to Mars is currently around $2 to $3 million. Now, if we have to take all the shielding with us, it's likely going to be prohibitively expensive. That's if the plan is to set up long term. Now, whilst I know that $2 to $3 million per kilo would be cost prohibitive to an entire human Mars mission, and the cost would have to dramatically come down before we even attempt something like this, payload cost is still going to be one of, if not the greatest limiting factor in a Mars human settlement. So the point does still stand. The fungus essentially becomes a biological shield, wrapping colonist living spaces in a layer of living, self-maintaining protection. It's the kind of unlikely solution only nature would come up with, not engineers. And I mean that with absolutely no disrespect to engineers, but they're probably not spending their days thinking about fungi. To be fair, who is? Alright, so it's a potentially promising form of radiation shielding, sure. But how could this mutant fungus terraform Mars? Well, not by itself. Now, terraforming is an incredibly large project, a slow burn of small, gradual changes over time. It isn't going to happen overnight no matter what anyone says. But this could be a great first step for a couple of actually quite interesting reasons. Now, right now, Mars is cold, sterile, and obviously bathed in dangerous levels of radiation from both GCRs, or galactic cosmic rays, and solar energetic particles, particularly the nasty high-energy particles released by solar storms. Now, radiotrophic fungi could form dark, melanin-rich biofilms on the surface of rocks or habitat walls. They'd soak up radiation, reduce local exposure, and even slightly warm the surface by darkening it. Now, melanized fungi are especially resilient to desiccation, the removal of moisture, and extended periods of extremely low temperature, like the freeze-thaw cycles that even the warmest areas of Mars experience. They are tough survivors that have specifically evolved to survive in extreme conditions. Now, it would be a small effect, but remember, large-scale climate change, which is what terraforming Mars would be, starts with small feedback loops. Now, where it starts to get really interesting is if we combine fungi with, say, oxygen-producing algae or cyanobacteria, we could build a symbiotic ecosystem. Now, fungi would shield and support, while microbes generate oxygen and biomass. The fungus becomes sort of the foundation layer, like the biological insulation. It could even be blended into building materials, fungal mycelium grown through Martian regolith to create biocomposite blocks that both support structures and attenuate radiation. You'd essentially have living architecture. But the potential of this fungus goes far beyond that even. Now, on Earth, fungi are sort of the unsung engineers of just about every ecosystem. Now, they recycle dead matter, unlock nutrients trapped in rock, and form symbiotic networks with plants through something called mycorrhizae, essentially microscopic partnerships where fungi trade minerals for sugars. Now, without these relationships, most plants would struggle to survive, and ecosystems as we know them just simply wouldn't exist. So if we can establish even a few hardy fungal species on Mars, especially ones that can tolerate radiation, dryness, and cold, they could start performing the same quiet bioengineering miracle there. Now, inside pressurized dome habitats, or what NASA calls human-assisted environments, where temperature and moisture can be controlled, these fungi could kickstart the chemistry of soil itself. Now, Martian regolith is rich in minerals, but almost completely sterile. No microbes, no organic carbon, and almost no available nitrogen, which is one of the most essential elements for plant growth. Fungal activity could begin to change that, though. Now, as the fungi grow, they excrete organic acids that slowly weather the rock, releasing elements like phosphorus, potassium, and iron. Now, their biomass would add carbon compounds to the mix, turning inert Martian dust into the beginnings of real soil for agriculture. And here's where it gets even more interesting. Now, certain fungi can also host or even fix nitrogen indirectly by living alongside nitrogen cycling bacteria. Now, together they could start enriching Martian soil with the nitrates and ammonium that plants need to grow. Now, that's the first step towards sustainable agriculture, farming that doesn't rely on constant chemical input from Earth. This isn't just helpful, it's absolutely essential to a self-sustaining colony on Mars. Now, if you want people to live there, they need to be able to grow their own food. Imagine a greenhouse on Mars where the walls and the soil are both alive, a self-sustaining ecosystem where waste becomes fertilizer, oxygen comes from photosynthesis, and the fungi keep everything in a sort of chemical balance, just like they do on Earth. It's not fantasy, it's just clever ecosystem engineering at the microbial level. And further down the line, maybe centuries from now, if those same radiotrophic fungi can eventually survive in the open under, say, protective biofilms, for instance, they could begin to seed the Martian surface itself, creating dark biological crusts that trap warmth, stabilize dust, and hold tiny pockets of moisture. It would be the very beginning of Martian soil ecology. Not terraforming in the cinematic sense, but the patient, biological, real-life version. Life preparing the way for more life. Now, I think there's something particularly beautiful about that something born from one of humanity's worst mistakes could seed life on another planet. Okay, now here comes the healthy reality check, because if you've been paying attention, there were a lot of coulds in everything I just said. Now, Cladosporium's sphaerospermum is amazing, no doubt, but it isn't magic. It isn't a silver bullet. Now, radiotrophic fungi don't eat radiation in the way you might imagine. The energy yield is very small, enough to enhance survival, but it isn't the primary driver of growth. They still need organic nutrients, carbon sources, nitrogen, and water. They're also slow. Building a 20 centimetre thick wall of fungus would take time, and you'd have to balance it with air circulation and humidity control. And while melanin is great for blocking radiation, it's not perfect. To be strictly technically accurate, it attenuates radiation rather than stops it outright. Now, Martian regolith also has other nasty chemical issues which would also have to be addressed before it could be used to grow food, particularly the perchlorates. A realistic full habitat on Mars would likely combine regolith shielding, water tanks, and biological layers like radiotrophic fungi. Basically a hybrid system which could work together. But the point is, for the first time we have a living material that actively reduces and uses radiation. One of the environmental factors we've never really had a fantastic solution for. And that's something we'll need if we want to stay on Mars or anywhere else in our solar system long term. In the ruins of a shattered reactor, life found a way to turn death itself into energy. A symbol of destruction and human hubris has become a symbol of adaptation and new life. A reminder that nature is clever, and not all engineering solutions need to come from engineers. Every now and again, nature enters the chat to show our best and brightest up, and that's a good thing. Interplanetary colonisation is a huge project, and we need all the help we can get, because it isn't just humanity that benefits from this. It's all the life we'll take with us too. Plants, animals, bacteria, microbes, and fungus. Now, if you liked or found this video interesting, go ahead and click on one of my other videos that should be popping up on the screen in a minute. And if you like those, I want to see more, and invite you to go ahead and hit the sub button. I know I've had a couple of months off recently. I apologize. Partly just due to time of the year, crazy season, but to be honest, I also spent a fair bit of time pretty much redoing my whole setup in my studio here. New camera, new mic, ripped out and replaced all the LEDs and the backdrop, complete nightmare, etc. But I'm back now. I have a few videos I'm working on at the moment, which I'm really excited about. A couple of bigger projects, but for the short future, I'm going to reduce to uploading probably once a month instead of every 2 weeks. To be honest, I'd prefer to deliver one well-researched long-form video per month while I'm getting the ball rolling again, rather than just rushing out to lesser quality videos. But I will get back to fortnightly uploads shortly, now that I've got everything in here working a little bit better. Anyway, that's it for me. Thanks for watching, have an awesome week, and I'll see you next time.